Hi everyone, welcome to lecture 22 on Bayes' theorem. The objectives for this video are the following. After watching, everyone should be able to, number 1, state and prove Bayes' theorem, and number 2, apply Bayes' theorem to some concrete examples. So the subject of this video is this thing, Bayes' theorem, where we're going to be putting more of our probability work to good use. The key takeaways are those to be able to state, prove, and apply it. So let's dive straight in and have a look at what it is. Bayes' theorem is a mathematical formula used for calculating conditional probabilities. If P and Q are statements, Bayes' theorem tells us how the probability of Q conditional on P and the converse, the probability of P conditional on Q, are related. These two probabilities are not always equal. Now, the theorem has lots of philosophical significance that unfortunately we don't have time in this course to touch on, but I'll mention it here in passing anyway. The theorem figures prominently in this thing called subjectivist or Bayesian approaches to epistemology, statistics, and inductive logic. Subjectivists, who are people that maintain that rational belief is governed by the laws of probability, lean heavily on conditional probabilities in their theories of evidence and their models of empirical learning. Bayes' theorem is central to these enterprises because it simplifies the calculation of conditional probabilities and because it clarifies significant features of the subjectivist position. The cornerstone of the theorem is this, that a hypothesis is confirmed by any body of data that its truth renders probable, which in turn forms the cornerstone of all subjectivist methodology. So what we're going to do is look first at how to prove the theorem. There are several different forms of the theorem, and I'll ask about that a little bit in the assignments. They all say the same thing, of course. And the one we'll prove in this video is this one. It says, let P and Q be statements with neither P nor Q having probability 0. Then the probability of Q given P is equal to the probability of Q times the probability of P given Q, all divided by that thing on the bottom. The probability of Q times the probability of P given Q plus the probability of not Q times the probability of P given not Q. Now notice that we can immediately see that it lets us calculate the conditional probability of Q given P in terms of the conditional probabilities with P and Q, or P and not Q, reversed, so switched over. That's why the theorem relates the two conditional probabilities P of Q given P and P of P given Q. Now, while it might look like there's quite a bit going on here, the proof of the theorem is not so hard, so let's see how we derive it. We start with the definition of conditional probability from a few lectures ago. That definition is this. Let P and Q be statements of non-zero probability. The probability of Q given P is the probability of P and Q divided by the probability of P. Now we notice a few things. First thing we notice is that P is logically equivalent to the complex statement P and Q or P and not Q. This, of course, can be checked using truth tables, and since those two statements are logically equivalent, they are assigned the same probability. So substituting the complex statement in for P in the denominator, we see this, that P of Q given P equals P of P and Q over P of P and Q or P of P and not Q. The second thing we notice is that P and Q and P and not Q are mutually exclusive. This again can be checked using truth tables, and so in light of that we can apply the special disjunction rule to the complex statement in the denominator. And doing that we obtain P of Q given P equals P of P and Q divided by P of P and Q plus P of P and not Q. The probability of a disjunction of mutually exclusive statements, remember, is just the sum of the individual probabilities. And the final thing we notice is the following. If R and S are statements with non-zero probabilities, then by the definition of conditional probability again, P of S given R is P of R and S over P of R. And rearranging that, we see that P of R and S equals P of R times P of S given R. And now we make the following substitutions. Since P and Q have non-zero probabilities, we can substitute P in for S in what we've just written and Q in for R in what we've just written. Doing that, we obtain P of P and Q equals P of Q times P of P given Q. And we can also make another substitution. We can also substitute P in for S in equation 1 and not Q in for R in equation 1. And doing that, we obtain another equation, P of P and not Q equals P of not Q times P of P given not Q. Now the last thing we do is look at equations 2, 3 and the one labelled with a star down there. Since there are probabilities of conjunctions in equation star, we can substitute in what we've derived in equations 2 and 3 for those conjunctions. And when we do that, we obtain this. P of Q given P equals P of Q times P of P given Q divided by P of Q times P of P given Q plus P of not Q times P of P given not Q. And that is the theorem, so we are finished with the proof. Now I'd encourage everyone to write this out a few times along with the justifications of each step to the side like I've done here. I would do this until you can do it without the video alongside it, so you can do it from memory. Now the next thing we'll do is apply the theorem to a concrete example. So here's the theorem again. A typical problem that asks you to apply the theorem will involve you calculating all the probabilities that are on the right hand side so you can figure out what P of Q given P is, so you can figure out what the left hand side is. So let's have a look at an example where we do that. Here's the problem. The probability that Pen will study for the test is 0.4. The probability that she'll pass, given that she studies, is 0.9. The probability that she passes, given that she doesn't study, is 0.3. So the question is, what's the probability that Pen studied, given that she passes the test? So the first thing to do is identify the statements in the problem. We're interested in this. P of Pen studied given Pen passes. So the statements are that Pen studies for the test and Pen passes the test. If we compare this to the theorem, we're letting Q be the statement Pen studies for the test and P be the statement Pen passes the test. And using the theorem, we can see what we need on the right-hand side to calculate the probability of interest. The first thing we need is P of Q, which in our context is the probability that Pen studies for the test. This information is given in the question, so we know that P of Pen studies is 0.4. The next thing we need is P of P given Q, which in our context is the probability that Pen passes the test given that she studies. This is also included in the problem. So P of Pen passes given that she studies we know is 0.9. Now at this point we can calculate the numerator, so let's look at the stuff in the denominator. The first pair of probabilities we need is P of Q and P of P given Q, which in our context is the probability that Pen studies and the probability that Pen passes given that she studies. Again, all of these probabilities are contained in the problem, so we know that P of Pen studies is 0.4 and P of Pen passes given that she studies is 0.9. So we can calculate that first part of the sum in the denominator. The last thing we need is P of not Q and P of P given not Q, which is where we do a tiny bit of work. So first let's think about P of not Q. This is where the work is, but it's super easy. We have P of Q, remember, or the probability that Penn studies is 0.4. So using the negation rule, P of not Q, or the probability that Penn doesn't study for the test, is 1 minus 0.4, which is 0.6. The last thing we need is P of P given not Q, or the probability that Penn passes given that she doesn't study, and this again is given in the question. The probability that Penn passes given that she doesn't study is 0.3. So we have everything we need to calculate the right hand side, and if we substitute in everything we've worked out, we get this. P of Penn studied given that she passes equals 0.4 times 0.9, all divided by 0.4 times 0.9 plus 0.6 times 0.3. And if we put all that into a calculator in the right way, we get that the probability that Penn studies, given that she passes, is 0.36 over 0.36 plus 0.18, which is 0.67, or more precisely, it's 2/3. I've just rounded it here. Now, this example was easy in the sense that most of the information needed to solve the problem was given to you in the question, and that won't always be the case, so let's look at a slightly more involved example. Here's the theorem again. Now, in the version we've proved, we look only at the statements Q and not Q. That is, we assumed that in terms of Q, there were only two possibilities. Either Q is true or it's not. However, we can sometimes partition the space of possible outcomes into more than just two events, like Q and not Q. And if that's the case, instead of just Q and not Q, we consider n mutually exclusive and exhaustive statements, Q1, Q2, and so on, all the way up to Qn. Now, it's essential that these are mutually exclusive and exhaustive. That's what I mean by partitioning the space of outcomes here. Exactly one of the Q's is true at any one time. Now, in that case, one can prove that the simple statement P is logically equivalent to the complex statement P and Q1, or P and Q2, or P and Q3, or, and so on, or P and Qn. Before, we had just two of these Q's, that is, we had Q and we had not Q. Now, though, we're considering any finite number of them. And if we carry out the proof of the theorem in exactly the same way that we did for two statements, then the result is this. For any I between 1 and n, P of Qi given P equals P of Qi times P of P given Qi divided by P of Q1 times P of P given Q1 plus P of Q2 times P of P given Q2 plus, and so on, plus P of Qn times P of P given Qn. This thing is what we call the general form of Bayes' theorem. It's proved in exactly the same way as the version we proved before, where there were only two Qi's. Now, I ask you to prove this general version on the assignments, and more complicated examples will require you to use this version of the theorem. So to make sense of all the algebra that's on the screen here, let's go through one of those more complicated examples. Suppose we've got 3 jars, and the jars are filled with balls. Jar 1 contains 6 red balls and 4 black balls. Jar 2 contains 9 red balls and 1 black ball, and jar 3 contains 5 red balls and 5 black balls. Suppose someone draws a ball from one of the jars, but you don't know which jar they've drawn it from. They give you the ball, and you look at it, and you see that it's red. And then the question is, what's the probability that the ball came from jar 2? So let's break this problem down. Because you've seen that the ball is red, the question is asking you for the probability that the ball was drawn from jar 2, given that it's red. The information you've learned, remember, is that the ball is red. However, we don't just want to label the statement the ball was drawn from jar 2 as Q and use the version of Bayes' theorem that we used in the last example. And the reason for that is because if we did, then we would have to consider what not Q means in this example. Not Q would mean the ball did not come from jar 2. And in our context, this means the ball comes from jar 1 or it came from jar 3. So if we're to keep things simple, what we're going to do is partition the space of outcomes into 3 mutually exclusive and exhaustive events instead of 2 like we did last time. And here outcome 1 is that the ball was drawn from jar 1. Outcome 2 is that the ball was drawn from jar 2. And outcome 3 is that the ball was drawn from jar 3. So there are 3 possibilities here, not 2 like there was in the previous example. And this means that we need the version of Bayes' theorem with 3 mutually exclusive and exhaustive events. So we need this one. P of Qi given P is P of Qi times P of P given Qi divided by P of Q1 times P of P given Q1 plus P of Q2 times P of P given Q2 plus P of Q3 times P of P given Q3. So now we've got the setup and we can start to label things in a sensible way. We're interested, remember, in the probability that the ball came from jar 2 given that the ball is red. So to label things, let's let Q1 be the statement the ball came from jar 1, Q2 be the statement the ball came from jar 2, and Q3 be the statement the ball came from jar 3. And P, of course, is the statement that the ball is red. Now we can start calculating. So the theorem in our context tells us this, that the probability the ball came from jar 2, given that it's red, is the probability that it came from jar 2 times the probability that it's red, given that it came from jar 2, all divided by the probability that it came from jar 1 times the probability that it's red, given that it came from jar 1, plus the probability that it came from jar 2 times the probability that it's red, given that it came from jar 2, plus the probability that it came from jar 3 times the probability that it's red, given that it came from jar 3. So we have to calculate all these things on the right hand side. So let's start by looking at the things in the numerator. First, what's the probability that the ball came from jar 2? Well, the question tells us that there are 3 jars, each with an equal amount of balls in them, and so the probability the ball came from jar 2 is 1 out of 3, or 1/3. Next, we ask what's the probability that the ball is red given that it came from jar 2. So here we're focusing our attention on jar 2. The question tells us that jar 2 contains 9 red balls and 1 black one. So the probability that the ball is red given that it came from jar 2 is 9 out of 10, or 9/10. Now I've used a shortcut here instead of explicitly carrying out the formula to calculate that conditional probability, but if you want to be 100% rigorous, you would use that definitional formula to get this result here. So now we've got everything in the numerator, so let's look at the denominator instead. The first thing we need is the probability that it came from jar 1 times the probability that it's red given that it came from jar 1. Well, the probability that it came from jar 1 is 1/3, because we said there are 3 jars and they've all got the same amount of balls in them. And to calculate the probability that it's red, given that it came from jar 1, we focus our attention on jar 1. The question tells us that jar 1 contains 6 red balls and 4 black balls, so the probability that the ball is red, given that it came from jar 1, is 6/10, or 3/5. Next, we need the probability that the ball came from jar 2 times the probability that it's red given that it came from jar 2. And this, we notice, is exactly what the numerator is, so in fact we've already calculated these values. The probability that the ball came from jar 2 is 1/3, and the probability that it's red, given that it came from jar 2, is 9/10. And finally, we need the probability that the ball came from jar 3 times the probability that it's red, given that it came from jar 3. And well, we see that the probability that it came from jar 3 is 1/3 again, by the same reasoning. There are 3 jars and they've all got equal amounts of balls in them. And finally, to calculate the probability that it's red, given that it came from jar 3, we focus our attention on jar 3. The question tells us that jar 3 contains 5 red balls and 5 black balls. So the probability that the ball is red, given that it came from jar 3, is 5/10, which is 1/2. So now we've got everything we need on the right hand side. Looking back at the theorem, we can substitute in everything we calculated. And doing that, we see that the probability that the ball came from jar 2, given that it's red, equals 1/3 times 9/10, all divided by 1/3 times 3/5, plus 1/3 times 9/10, plus 1/3 times 1/2. And if we calculate those values, we find the right-hand side is equal to 9/30 divided by 3/15, plus 9/30, plus 1/6. And any calculator, or your head if you do it right, will tell you that this whole thing is equal to 9/38, which is 0.24 when we round it. So that is how we apply Bayes' theorem in more involved examples where the total possibility space involves more than 2 statements. There'll be plenty of these on the assignments of a range of difficulties. This one we've done together though should help. If it looks kind of overwhelming, then going through it slowly, step by step, is a big help, even starting by labeling your statements so you can see what to do when you look at the theorem, which involves, of course, only P's and Q's, as we've seen it here. And again, practice makes perfect with this stuff. So we've seen Bayes' theorem, which is what I think the most important thing in this course, and it's something I'm looking for people to really take away from this course as well. Next time, we'll finish up chapter 6 by discussing probability and causality. So have a go at your self-reflection questions, and I'll see you next time.